You have an exam that begins tomorrow and ends on Friday. So I wrote it. It's 20 questions long. I know some of you are uncomfortable with 10 points per question. It's relatively high stakes. An equal number of you are uncomfortable with exams that are like 40 questions long. So what are we going to do? In any case, it's multiple choice. Read the questions carefully. As you know, some of the questions are select all that apply. I know you love that one in particular. Just so you know, for select all that apply questions, I don't apply any partial credit, at least not at the beginning, because I don't want you to gamify the system and just color in all the answers and then get all the credit. So only select the answers you think are correct. We'll deal with partial credit after the fact. Are there any questions about the format of the exam? Okay, well, good luck to you. Pay attention to the hours that the testing center is open. They are different in spring term than they are in fall winter. So I don't want you to show up at like 8 o'clock and discover that nobody's there and nobody has been there for hours. So just pay attention to that. Okay, well, one thing we didn't, that I realized we didn't do that we need to is a small reaction from chapter 14. You'll recall that in chapter 14 we used aldehydes and or ketones to take amines, in this case a primary amine, and some acid catalyst. So this isn't new, this is review. Sometimes this will be like acetic acid. You don't need a very strong acid to do this, but we will create imines. And we talked a little bit about imines. Of course, if you use a secondary amine, you get what's called an enamine as your product. But we'll just stick with the imine for now. We didn't talk at all about what you can do with an imine, but in terms of reactivity, you should think of the imine as kind of like, that's not an at, that's an A, kind of like a ketone or an aldehyde. What that means is it's an electrophile, and it can react in the same way that aldehydes and ketones react. This could react with organolithiums or Grignards, and it could also react with reducing agents like sodium borohydride or lithium aluminum hydride. The one one example of this would be if you used sodium borohydride. This is going to deliver a hydrogen, and remember that we generally use sodium borohydride with some kind of protic solvent. This is going to deliver a hydride to the carbonyl carbon in the same way that we would do this for a ketone. I'll just draw you this quickly. Delivery of the hydride to the carbon nitrogen pi star, breaking of the carbon nitrogen pi bond, probably at the same time to avoid buildup of negative charge on the nitrogen, which is really unstable, probably at the same time as we're breaking the pi bond. The lone pair on the nitrogen picks up a hydrogen from solvent. But the effect is that we have reduced the imine to its amino or amine form. Okay? So this is a convenient way to make regular amines. You start with a ketone, you add a primary amine, and then you reduce the corresponding imine to give you the amine. Yes?
I remember reading a textbook that lithium aluminum hydride can reduce amides into amines. Can anything else do that, or is that just lithium?
Your book said lithium aluminum hydride could reduce amides to amines, and that's right. Sodium borohydride does not. It's not reactive enough. This was not a reaction we spent a lot of time on. You should be aware of it if you need it in synthesis questions. I did not show you the mechanism of that reaction. Okay, so this two-step reaction series is sometimes called reductive amination, and it's a highly synthetically useful way to get amines. It's a workaround to an issue that I may or may not have been talked about in 351. I'll just mention it briefly. One problem, you might ask the question, could you not use a reaction like this, an SN2 reaction, to make the same amino compound? And the answer is not very well, because it turns out the more alkyl groups you add to an amine, the more nucleophilic the corresponding amine is. If the product here is more nucleophilic than the starting material, the product is going to start competing with the starting material for remaining reagent. And in the case of, trying to do substitution reactions with amines, you often end up with what are called over-alkylated products, where with each alkyl group you add more nucleophilicity to the product, and over-alkylation is a classic problem in attempting to do amine alkylation via an SN2 reaction. Reductive amination sidesteps this completely because when you do the imine formation, you can only make the imine once. There's no, the lone pairs on the nitrogen after you form the imine aren't going to go attack another carbonyl. There you stop, having added one group to the nitrogen, and then you reduce it to an amine, and that prevents over-alkylation. By the time you get to the amine, there's no more electrophile present. So this is a nice sidestep, a nice way to prepare amines. And again, you should be good at imine formation. All we're doing is applying a reducing reagent to the imine, so that's not new either. What's new is the combination of those two. Okay? Yes?
In this case, we're only adding hydrogen. Is there a way to kind of add more alkyl groups?
To add, sorry, say that last part again.
To add more alkyl groups?
Yes, you can react imines. I didn't show you that here, but you can react imines with organolithiums and Grignards. The products would be entirely predictable. There'd just be an R group here. Okay, with that, we turn our attention to chapter, 16 at this point, which is the chemistry of carboxylic acid derivatives. And as you've just read in King Benjamin's speech, how he cannot tell you all the ways and means by which you can commit sin. I also can't tell you all the ways and means by which you can do chemistry with carboxylic acid derivatives. For example, I'm not going to go through one by one all the possible things you can do with an acid chloride. And by nucleophiles here, we are talking about, let me give you some examples of course, you've seen acid chlorides react before with reducing agents and organolithium reagents. Here, for nucleophiles, what we're talking about are alcohols and amines and carboxylates. Potentially also thiols. But these kinds of nucleophiles do substitution, nucleophilic acyl substitution reactions on acid chlorides. That is, you could have, say, let's do the amine, attack the pi star to get a tetrahedral intermediate. That would look like this. There are a couple different ways you could show these next steps. You probably at this stage can just have the electrons on the oxygen kick the good leaving group off. The chloro is a better leaving group than the positively charged nitrogen. And then after the fact, some base, your text will probably show Cl minus, removing the hydrogen from the amine to give, from the nitrogen to give you the amide product. Okay? Now, you should not need me to draw for you the mechanism for reaction of an alcohol with an acid chloride to get an ester, right? It's the exact same thing. You should also not need me to draw you the mechanism of attack of a carboxylate on an acid chloride to give you an anhydride, or attack of a thiol on an acid chloride to give you a thioester. All of those are variations on the same basic theme. The other thing you should realize is that the reason these reactions can work is because in each case, the nucleophile that we're bringing in, the thiol, the alcohol, the carboxylate, the amine, they are all poorer leaving groups than the chloro that leaves, which is why this happens. This is why this reaction can happen, okay? So you should be able to do that. There should be practice problems that help you with that. We don't have a lot of time to spend on things that are easy today, so we're going to move on from that. But I'll pause for questions. Yes?
We don't have to protonate the carbonyl oxygen when we're attacking with an O because there's a chloro on it, correct?
With the acid chloride, this is electrophilic enough that we don't need to activate the carbonyl by protonating it first. You will see that for some of the other reactions that we do today, we need an acid catalyst to help things along. I'll also maybe point out that sometimes experimentally, if you actually do these reactions in the lab, sometimes you actually do need to add a base to help out with the proton transfer, either before or after the reaction happens. What I've shown you here is sort of a general mechanism. But in specific cases, you might need a base to have the reaction happen. I saw another hand.
Just making sure that we don't need to remove and duplicate the amine group either. Because chloro is a better group.
So the idea is, does chloro leave first because it's a better leaving group? I would be very comfortable if someone showed removing the proton from the amine first. You could do some kinetic experiments to try to determine whether chloro leaves first and then you deprotonate, or whether you deprotonate first and then chloro leaves. That level of detail probably doesn't matter. They definitely happen in separate steps. As to which happens first, I don't think it matters. Yes?
Is using pyridine in adding an alcohol to an acid chloride just to replace something that would smell deadly with something smelly? Or is it
So yeah, I think, and I'm not totally sure if this is in your text or not. As I said, sometimes this base your text tries to keep things simple, but when you actually do experiments in the lab, you sometimes figure out that they are not simple. For example, Cl- is not a good base. It's the conjugate base of a strong acid, but sometimes it's simple just to use it because it's there. In some cases, you will need, as I said, to add a base to help the reaction go. Pyridine is one such base. If you see it in a practice problem, that's what it's doing. I promise I have not written any questions on the exam where the difference between the right answer and the wrong answer is the presence or absence of pyridine, a base, okay? But if you see it, don't be distracted by it, and please do understand what's going on. Okay. I could show you similar things for the anhydride. You can use the anhydride in much the same way as you use an acid chloride. You can, for example, take an anhydride and react it with an alcohol or an amine. Usually you need a base to make this happen, but in any case, you can react an anhydride with an alcohol or an amine to get the corresponding ester or amide. I think you can get that without a lot of help from me, so I'm going to move on from there. What I want to spend most of our time talking about is the tricky stuff, which is how do you do chemistry with carboxylic acids. Before I do that, let me just add something that I remembered from the text. Sometimes when you're reacting an acid chloride or an anhydride with an amine, sometimes your text will put in parentheses after the amine excess. What they mean by that is you need one equivalent of the amine to attack the carbonyl compound. You need the second equivalent of the amine to act as a base in this step to remove the hydrogen. That's all that's going on there. Don't be distracted by it, but do understand what's going on. Okay. So we've talked about acid chlorides, we've talked about anhydrides. Let's talk about esters. Esters are less reactive than acid chlorides and then anhydrides, because OR minus, just the unstabilized alkoxide leaving group, where R is basically something alkyl, generally not a good leaving group, meaning that esters are less electrophilic than anhydrides and acid chlorides. So you might expect reactions involving esters to require more strenuous conditions or to require some kind of catalyst to help the reaction happen. And this is true. So I'll show you a couple of reactions that I want you to be aware of. The first is called, both of them are examples of hydrolysis reactions of esters to carboxylic acids. The first is under basic conditions. The reaction is hydrolysis, meaning using water to break the bond between the carbonyl carbon and the oxygen, OR oxygen of the ester. Hydrolysis of the ester. This reaction is sometimes called saponification, and that's from, I don't know if it's Latin or Greek, for soap. This reaction was used by our ancestors to make soap, and I'll show you how that works after I show you the reaction. Usually by basic conditions we mean potassium hydroxide. So I'll use the methyl ester just so we have something that isn't an R there to look at. The reaction conditions are potassium hydroxide. Hopefully you're getting good at knowing when to ignore the counter ion, and you see this as just OH minus. Potassium hydroxide is sometimes sold or known as lye, which is how your ancestors would have known it. You can get it from wood ash. So anyway, the negatively charged oxygen, let me just say actually the products of this reaction are the carboxylate and then the alcohol, the OR group from the ester ends up leaving as the alcohol. One of the oxygens of the carboxylate comes from the OH of the reagent. A negatively charged oxygen, like hydroxide, is a strong nucleophile, so that's going to be good enough to attack the carbonyl carbon directly. One reason you can tell this is a reasonable step is because you go from starting materials where you had a negatively charged oxygen to products where you also have a negatively charged oxygen. So in terms of stability, negatively charged oxygen here, negatively charged oxygen there, should be about similar, and it is. Now, a negatively charged oxygen is, well, we're in a situation here where we have the tetrahedral intermediate. We'll call this the alpha position because you've got two potential leaving groups, which I'll sort of underline in green. And at the beta position, you have a negatively charged oxygen with a lone pair. And what do we do here? We've talked about leaving groups. And you're used to thinking of OR minus or OH minus as poor leaving groups, and they are. They're certainly poorer leaving groups than Cl minus, and if we had a Cl here, we would have Cl do the leaving. But when we're dealing with a tetrahedral intermediate, the thing that really determines whether a leaving group can leave or not is a comparison to the negatively charged oxygen that's the kicker offer. The leaving group needs to be at least as good as a negatively charged oxygen. What I'm saying is it's totally reasonable for a negatively charged oxygen to kick off another negatively charged oxygen as a leaving group. That shouldn't be a surprise. We're trading one negatively charged oxygen for another. It would be totally unreasonable for a neutral oxygen to kick off a negatively charged oxygen. Notice that we have two potential leaving groups. If we kick off the OH minus, that's just the reverse reaction step that would take us back to starting materials, and that probably happens. If instead we kick off the OR minus group, that will give us the following product. Okay? Now, I'm actually going to erase the reversible arrow here because there's something else that happens to these two products from this step of kicking off a leaving group that prevents the backwards reaction. And that is this. Notice that the proton now on our product is acidic. This is a pKa of around 4, carboxylic acid proton, whereas the proton on our alcohol product has a pKa of 16. So this is no-brainer chapter 2 stuff from 351, except 12 is not the same as 16. What happens at this stage is the thing that just left deprotonates the carboxylic acid. That equilibrium constant is greater than or equal to a factor of 10 to the 12. That's effectively irreversible, all right? Which means that deprotonation of the carboxylic acid is the major downhill in energy step that pushes this reaction forward to products. Okay? Any questions about that? Yes?
It seems like this is definitely like a rate determining step in this reaction. Are there any other rate determining steps that you really want us to know for the testing of this
Kinetics of carbonyl chemistry, we haven't actually talked about what the rate determining step is, and we won't. There's a lot of work done in that, but no, we won't be dealing with that. Yes?
In acetal formation, we have to protonate first before we attack with the O group.
Right.
Can you explain one more time why one is different?
So when we did acetal formation, we protonated first. Remember that our nucleophile in acetal formation was an alcohol, neutral oxygen. So a neutral oxygen can't attack a carbonyl directly. We need to protonate first. I suppose you could have asked the question, can I not make an acetal by using this? The answer is you could, but it actually isn't that productive. If you use the alkoxide to try to make the acetal, you could get to this intermediate, and perhaps you could pick up a proton but remember, acetal formation requires this oxygen to kick off the leaving group. And under basic conditions, a neutral oxygen can't kick off a negatively charged oxygen. So in order for this to leave, you have to protonate it first, and you can't do that under basic conditions. What I'm telling you is, if you try to make the acetal from the alkoxide, at best, you get the hemiacetal, which is not that stable. So you just go right back to starting materials. Yes?
So just making sure in the reaction of, if we were in acidic conditions, it would perhaps would make sense for us to protonate that leaving group before that?
Right, and we will do actually, I'll just defer to like 2 minutes from now where we're going to do acid catalyzed hydration of esters. Yeah. Okay, others? Yes?
So is that overall reaction then not reversible because it's so down?
Yeah, that reaction is overall not reversible because that last step is so downhill in energy. Okay, and just, so this is called saponification ester hydrolysis. Just as a little connection to all of our collective past when people had to make their own soap instead of going to Target or wherever, you would take animal fat. Here's a triglyceride. Triglycerides involve alcohols, a 3-carbon alcohol called glycerol, in which each of the alcohol oxygens is tied up in a long chain, in an ester with a long chain carboxylic acid, 6, 8, 10, 12, 14, 16. And then our ancestors would do this saponification reaction with lye. That's going to release the 3-carbon alcohol called glycerol. This is water soluble. You can isolate it and do things with it. But what our ancestors were after when they were making soap was actually the carboxylate. And this long chain fatty acid then, as you will recall from 351, has a polar head group and a non-polar tail. And the hydrophobic effect actually causes this to self-assemble into a micelle, which you've seen before. The exterior, it's a sphere. The exterior of the sphere is these polar head groups. The interior is this non-polar tail. This is a way of solubilizing grease, and this is how soap works. Okay, so saponification or soap making. All right, there's more we could say about that. Do we dare? Maybe not now. Let's, maybe I'll come back to some biological stuff if we have time. What I want to do now is talk about ester hydrolysis under acidic conditions. And we're going to kill 2 reactions with 1 stone here, because what I'm going to show you is that ester hydrolysis under acidic conditions is going to be very much like acetal hydrolysis / acetal formation. That is, we can hydrolyze esters under acidic conditions with an excess of water. We can also do the backwards reaction where we start with a carboxylic acid and an alcohol and use acidic conditions to make the ester. As we saw with acetals, the key is going to be whether we're removing water or providing an excess of water. I'll show you ester hydrolysis under acidic conditions, and then we'll go through it the backwards way. So we'll start with the same ester. You need some aqueous acid, okay? Where you, by virtue of the fact that you're an aqueous solution, have an excess of water. Water, being neutral, is not a good enough nucleophile to attack the carbonyl carbon directly to give you a negatively charged oxygen. So your first step is, and I'll just be general here with HA, is to protonate the carbonyl carbon. I'm going to use equilibrium arrows because these acid-base equilibrium steps are, reversible. You're using an acid that has a pKa that's about the same as the pKa of this oxonium ion. Having activated the carbonyl carbon or carbonyl oxygen, a neutral nucleophile, a weak nucleophile like water, is a strong enough nucleophile to attack the carbonyl carbon. This is going to generate a tetrahedral intermediate. Notice you should feel okay about this tetrahedral intermediate because effectively we have traded one positively charged oxonium ion for another. I use the reversible arrows because at this stage you have a good leaving group in the form of water here, and you have neutral oxygens. A neutral oxygen is a good enough kicker offer. I'm just going to use green as we've done to sort of underline the potential good leaving group. Here's the alpha carbon, here's lone pairs at the beta position. Frankly, we have some here too. It would be totally reasonable for the lone pairs on this oxygen at the beta position to kick off the leaving group. And they do, and that's simply the reverse step, okay? So if we want something different to happen, we've got to stop the water from being a good leaving group. I know that students are uncomfortable in reactions when there are multiple things that could happen. You tend to think, well, how am I supposed to know? The thing that gives you a clue as to what's going to happen here is that you have an excess of water, which should tell you that the backward step for kicking water off should be overwhelmed in rate by the forward step of having water add, just by Le Chatelier's principle, okay? So even though that backward step is possible, we're going to ignore it. If we want something else to happen, we're going to need to use our acid catalyst to trade around who's the good leaving group. So let's start by stopping water from being a good leaving group. We'll use the conjugate base of our acid to deprotonate that. That will get us to a tetrahedral intermediate that looks like this. It's going to have 2 OH groups on it and 1 OR group. Of course, we can now use the acid catalyst that's regenerated. It could totally protonate either one of these oxygens, these OH oxygens. That would effectively take us backwards to this intermediate. But again, the backward step in rate is going to be suppressed by the fact that we have an excess of water pushing us forward. So what if instead we protonate the OR oxygen? That would lead us to the following intermediate, where again you will see that we have a potential leaving group. which I'll underline in green. And then adjacent to that leaving group, we have two potential kicker offer atoms. So here's the alpha position relative to the leaving group. We have two identical oxygens at the beta position. I'm going to choose this one, but you could just as easily choose the other. Lone pair electrons kick down and kick off the leaving group. And that will lead us to our final product, well, almost to our final product, sorry, not quite there. That will lead us to the following species. Kicking off of a positively charged oxygen by a neutral oxygen should look reasonable to you because in effect you are trading one oxonium ion here for another here. The leaving group in this case was methanol. It would be totally reasonable at this stage for methanol to come right back in and attack the carbonyl carbon to take us to this intermediate. Again, that reverse rate is going to be suppressed by the fact that we've got an excess of water that's pushing us forward. Finally, to get to our product, we will regenerate the acid catalyst by taking the conjugate base of our acid, removing the proton from the oxonium ion, and that will give us the carboxylic acid product and then also the methanol, the R group from the ester. Okay? So this is acid catalyzed ester hydrolysis. Go ahead.
So when you're proteinating the OCH3, make sure that it doesn't protein one of the OH groups.
How do you make sure it doesn't protonate one of the OH groups? The fact is it does. And if you protonate one of the OH groups, you're simply going backwards, which happens. But the fact that we've got an excess of water is going to make the forward steps more efficient. Yes?
Sometimes the text of the leaving group leaves the carbocation. Is that always okay because that's just the resonance structure of the double bond?
Yes. So we'll answer that question with this intermediate here. Sometimes rather than show the influence of the kicker offer group, realize that's not a word, the text will show the leaving group leaving without any kicking offing, whatever, to give you this intermediate. Notice that this intermediate is simply a resonance structure of that one. So either, except that's not a negatively charged oxygen. So either way of pushing the arrows is fine. Go ahead.
I think in the text it also just kind of generally says proton transfer. Can we assume
Yes.
that proton transfer is those three steps, the modification of the leaving groups?
Right. So sometimes in the interest of condensing things and with the hope that you know what the text is talking about when they say proton transfer, your text will sometimes abbreviate that and skip over this step. When it says proton transfer, this is what's going on. Yeah. Yes?
Is there any case where it would drop the double bond and give two alcohols instead of
Is there any case where it would drop the double bond and just give you two alcohols? You're thinking of a potential product like this?
Yeah.
No, and the reason for that is that watch the number of bonds to oxygen. In both the ester, there are 1, 2, and 3, and in the carboxylic acid, 1, 2, and 3, there are 3 bonds to oxygen. Here, there's only 2. Going from this starting material to this product would be a reduction reaction. You need a reducing reagent to have that happen. Turns out what you just said is, if you go back to chapter 14, is what happens to an aldehyde in water. You form the aldehyde hydrate. You can get from an ester to an aldehyde. We learned how to do that. Chapter 13, that reagent is what? Dibol. Good. If you were blank on that, then, or the other one that's unpronounceable, if you're blank on that, then go ahead and review that. That may come up more than once in your very near future. How was that for ominous foreshadowing? Dun, dun, dun. I need to get my iPad outfitted with sound effects, like that I can push buttons for emphasis when I say things. All right, that's ester hydrolysis under acidic conditions. Now I'm going to show you a reaction that you do. If you're in the 353 lab, you may actually have already done this. The backwards reaction starts with a carboxylic acid and an alcohol, and it is called Fischer esterification. A lot of reactions in organic chemistry are named by saying what they do and then adding ication or ation at the end of it. So making an ester, esterification, making a soap, saponification. Now you can name reactions too. Reducification, no, we normally say reduction. Oxidizification. Anyway, let's do Fischer esterification. And I want you to pay attention to, when we finish drawing this, I want you to go back and notice that all of the intermediates are exactly the same. We've simply pushed the arrows in the reverse direction. As with acetal formation, when we do Fischer esterification, we're going to need to remove water. So let's just use, we'll use methanol as our nucleophile. Notice that, and we're going to need some acid catalyst. Again, you want to not use aqueous conditions, because if you supply an excess of water, you push the reaction towards the carboxylic acid. So you need to use organic solvent. You probably need to do this under anhydrous or removing water conditions. Your acid catalyst probably needs to be organic soluble, and a good potential acid catalyst that's organic soluble is para-toluene sulfonic acid. There are actually tons of these that you could consider using. The neutral alcohol is not a good enough leaving group to attack the carbonyl carbon directly. So first we have to use our acid catalyst to protonate the carbonyl carbon to make the oxonium ion. Notice how that is the reverse of the final step in acid catalyzed ester hydrolysis. Once you have the oxonium ion, the alcohol nucleophile can attack the carbonyl carbon to get a tetrahedral intermediate. Of course, at this stage, the acid catalyst could deprotonate the oxonium ion and go back to starting material. But if instead the nucleophile attacks the carbonyl carbon, we get this intermediate. Notice how that is the same as the corresponding intermediate in ester hydrolysis. That alcohol that just added in is currently a good leaving group. And you have neutral oxygens at the beta position that can act as kicker-offers to kick off that leaving group. If that happened, that would simply be the reverse step. The reaction is going to be pulled forward by the fact that later on we're removing water. What we need to do now is, since we're removing water, we need to actually trade who's the good leaving group using proton transfer. So rather than use my magic textbook proton transfer box, I will actually show you the proton transfers. So there's one of them, using the conjugate base of our acid to get this neutral intermediate, where notice that we can't really do anything here because neutral oxygens can't kick off negatively charged leaving groups. That's not reasonable. Before water can leave, we have to use our acid catalyst to convert one of those OH groups into a good leaving group, again with proton transfer. I don't know what happened there. Now we've used our acid catalyst to grease the wheels, so to speak, changing who the good leaving group is. Now at the beta position relative to the leaving group, we have kicker-offer lone pairs on either of these oxygens. Electrons kick down and kick off the good leaving group. This is the stage at which we are removing water. The product is this oxonium ion. You can see we're almost to an ester. Of course, at this stage, water could be a good nucleophile, a good enough nucleophile to attack the positively charged oxonium ion. That's why we're removing it. There are multiple strategies for removing water. One of them is distillation. I'm not sure if you do this in your 353 lab. Another way is to just use something in the reaction mixture that soaks up water. And there are a lot of techniques for doing that experimentally, which you can learn about another time if you ever do this. But by removing water, we are pulling, by Le Chatelier's principle, removing water lowers the rate of the backwards reaction and causes the reaction to move forward. Then all it takes to get our product is to use the conjugate base of our acid to remove the proton, thereby giving us the final ester product and restoring our acid catalyst. Okay? Yes?
So what's preventing the OCH from forming the pi star 2 steps back?
I'm this one?
No, 2 steps forward.
Oh, I'm sorry. What's to prevent the other oxygen from doing the kicking offing? It turns out that what you've just described leads to a resonance structure of what we drew above. And so it's got to be equivalent, and probably both things are going on. Probably both kicking offing is happening. Meaning, notice how if I do that, I get this, which is just a resonance structure of that. Both of those are totally acceptable. Okay, so that's Fischer esterification. And that's how we take a carboxylic acid and convert it into an ester. It's worth pointing out that there's a reason why if you want to take a carboxylic acid and convert it into an ester, you've got to use these acidic conditions. Tell me, why wouldn't it work to do this? By which I mean, why is that bad? Go ahead. Right, deprotonation reactions are fast. You have a strong base and a decent acid. Before the negatively charged oxygen on the alkoxide attacks the carbon, to the pi star, it's simply going to remove the proton. What we just did, actually what I just showed you, is actually the same thing as why the last step of saponification is not reversible. We don't make esters from carboxylic acids under basic conditions. It doesn't work because you just deprotonate the carboxylic acid. It turns out that with carboxylic acids, and if you want to do chemistry with them, that acidic proton is actually pretty problematic, and we have to have ways of dealing with that. Our first way of dealing with that was to use an acid catalyst, okay? And you can do that to form the ester. A question we could ask though is, what if you wanted to form an amide? Would an acid catalyst be a good way to take a carboxylic acid and an amide? Could we do something like we've done previously? And the answer is no, it's problematic. The first problem with trying to make an amide from a carboxylic acid is that if you just start again with the amide, the amine, and the carboxylic acid, you end up with that same dang proton transfer reaction that happens before the amine can even attack the carbonyl carbon. The second problem is, what if could I use an acid catalyst to protonate the carbonyl carbon first? And the answer is no, because the amine is more basic than the carbonyl oxygen. And so if you use an acid catalyst, the first thing you do is make the ammonium ion, and that shuts it down. It's no longer a nucleophile. So our traditional strategy our strategy that we've used so far for the carboxylic acid is just dead for trying to make amides. We need a workaround. There's multiple workarounds that we'll talk about. I think now's probably a good time for a break. So let's take like 5 minutes, and then we'll start in on making amides in about 5.